So this is the second part of using Newton's laws of motion, and in this example we're only going to do one. It's a really long example, so we're only going to do one, and we're going to combine using dynamics and kinetics. So just a quick review. Remember in unit 1 we assumed that acceleration was constant, so now we're going to use that the net force remains constant. And so generally you're going to be using that net force equals ma to calculate your acceleration, and then you use your acceleration in one of the 5 key equations to determine the other part. So often we're being asked for displacement or maybe a final velocity. So again, normally step one would be to use the F net equals ma equation, and that way we are solving for our acceleration. And then we use the acceleration in one of those 5 key equations to determine whatever it is. So again, usually in the example we're going to do, it's going to be to figure out d, or sometimes you're asked for your final velocity, something of that nature. And actually in our example we're going to calculate for displacement, and we're also going to have to calculate for v2. So here's our example, and again, it is a long one. For those of you who were in class when we did it, I have made a slight change to the time just so that we're not confused by the 5.5 and the 5.5 like we were in class. If you are not in my class and you don't have this example written down or downloaded from the course website, I would recommend pausing the video here, writing down the information, because I'm just going to keep flipping from slide to slide onto blank pages so that we can do our calculations, okay? So you are going to need this information. So I dealt with curling because we had gone curling as a class. So we have a mass and we have our first force. Okay, so she's traveling forward, so she pushes out with that hack and she moves for 5.5 meters. She then moves at a constant velocity for 3.4 seconds, and then she needs to slow herself down by dragging her foot. And when she does that, she has another net force. So like I said, we're generally going to use our F net equation to be able to calculate the acceleration. So part A is asking us to calculate acceleration. So in the first part of her motion, she's pushing back against the hack. So that means she hasn't moved. And if she hasn't moved, then we don't have to do any work for the acceleration. She has gone 0 meters per second squared. So that's her first acceleration. For the second part, so she is just pushed out of the hack. So let's draw that free body diagram. So she's not floating. So we have Fn and we have Fg, and then we have our applied force. And our applied force is 145 newtons. Okay, so she's going forwards. So our F net is equal to Fa, and F net we can always replace with Ma equals Fa. To figure out our acceleration, we're going to divide both sides by m. So acceleration is equal to 145 newtons divided by the mass, 56 kilograms. I'm just going to go over here to write my answer. So our A is equal to 2.59 meters per second squared, and she's traveling forward. All right, so we're going to clean slate. So for the third part, that is when she starts to drag her foot. And so again, let's draw a free body diagram. So we have her normal force, force of gravity, those are balanced out. Those lines aren't equal, but we know they balance out. And we have our applied force. So again, we're going to write an F net equation. So F net equals Fa. Replace F net with Ma. Divide both sides by mass, so we can calculate her acceleration. So we want to make sure that everything's going forward. So we're actually going to put that her backwards force in as a negative value. So negative 42 newtons divided by the 56 kilograms. So her acceleration is negative 0.75 meters per second squared forward. Okay, so she is actually decelerating, but when we go to the next part, we're going to be looking for her displacement values. And so we want to be calculating all of those displacements forward. So we're going to treat that as a negative forwards acceleration. And so that is telling us that she's slowing down, but she's still going forwards. All right, so for part B is asking us to figure out her displacement. And we have 3 different parts of her motion. So we have the first part where she's traveling, and it actually tells us her first displacement, so her D1 is 5.5 meters. It tells us that in the question. Okay, it says that she pushes off with a force of 145 newtons and travels for 5.5 meters. Okay, so that's our first displacement. We don't have to do any work. The second part of her motion is it tells us that she travels at a constant velocity for 3.4 seconds. So I'm going to call this second part, our D2, is the constant part of her motion. Okay. And her constant part of her motion happens for 3.4 seconds. Okay, and we know that during that time she's accelerating at 2.59 meters per second squared. So we know that information. So now, if you go and look at your formula sheet, there is no equation that will allow us to figure out her displacement only using time and acceleration. We need a velocity. And we know that initially, before she starts that motion, before she pushes off, her initial velocity is 0 meters per second. So if we actually go and find out her velocity just before that 3.4 seconds starts, then we can actually then use that information. So what we want is we want to figure out first what her V2 is. So that is just before that 3.4 seconds. So let's say like 3.3999 seconds. How fast is she going just at that point? So in order to do that, we're going to use that displacement because in that time, or just before that time, she's gone 5.5 meters. So the easiest equation to use is our V2 squared equals V1 squared plus 2AD. And if we rearrange that, we'd be taking the square root of everything on the other side. So V2, sorry, I've forgotten my arrows, is equal to, so that's going to be 0 squared plus 2. So she's gone the 5.5 meters, so that's why we're using that, because it's just at the end of that time. We want to know just how fast she's going right then. Oh, and sorry, I wrote it in the wrong direction, or wrong order. And we know her acceleration is 2.59 meters. So her V2 is 5.34 meters per second, and she's going forward. So just before that constant part of her motion starts, that's her velocity. She's traveling at the end of that 5.5 meters, which is her initial acceleration part. Her speed is going to be 5.34 meters per second forward. So what we're going to use that in this equation to allow us to figure out our displacement, because we now know what her speed is and she's traveling at that constant velocity. So constant means that acceleration is not happening anymore. So she's traveling at 5.34 meters per second for 3.4 seconds. So what is her displacement? So if we rearrange that equation, we would get D equals V times T. So let's go ahead and put our information in. So 5.34 meters per second times 3.4 seconds. So this is going to be her displacement for the second part of the motion. So we get 18.1 meters per second forward. So that is that constant speed displacement. So then the next part of her motion, the third part, is the slowing and stopping. Okay, so let's write down what we know. We know before she starts dragging her foot, she's going for 5.34 meters per second. We know she's coming to a stop, so that means we have 0 meters per second. And we know her acceleration is negative 0.75 meters per second squared. So what is her displacement? So if you go and you check your 5 key equations, there is an equation that allows us to calculate this, and it's the same equation that we used. You'll notice that we tend to use the same equations over and over again. So to rearrange for D, we would move our V1 over and subtract it, and then we would divide both sides by 2A. So let's go ahead and put our information in. So we have 0 squared plus, just going to erase the whole thing, it's easier. So we have 0 squared minus 5.34 squared all over 2 times negative 0.75. So when you rearrange all of that and solve, you get 19 meters forward for your D. So you would do 5.34 squared. This negative is going to make that answer negative, and then you're going to divide it by negative 1.5. So that's how you get your D3 being 19 meters. So the very last step, and I know you're thinking, aren't we done yet? But we're not. We need to add our displacements together. So way back, our initial displacement was 5.5 meters. Our second displacement was our 18.1. And our last one was 19 meters. So if you add those all up, we get 42.6 meters forward. But we should round that so that we only have 2 sig figs, so let's round it to 43 meters forward. So that is a lot of work, but that's what you're going to have to do for examples. So other examples that you're going to deal with in your homework are going to be things like skiing down a hill and you hit a flat part, so that's going to slow you down, and then you start going downhill again, and so you speed up. So always break the motion into its different parts and then see what you can solve. And remember, a lot of times you're going to have to calculate that final velocity just before you change your motion. So at the beginning there, in the second part, we had to calculate how fast was she going after that initial part. And then we knew she was traveling at a constant velocity, so we could use that V2. Okay, and then we use it again in the third part because before she started slowing down, that's how fast she was going, and then she slowed down to a stop. So I know these problems can be tricky. You really need to do your practice. You need to follow along with the questions that are in your book, and if you need to come in for some extra help.